Okay friends, welcome to this class of plate tectonics. If you remember our last class, we are talking about this continental drift, and today we will continue the discussion regarding the other evidences of this continental drift. If I summarize the last class, we are talking about these continents, they are drifting apart, and you can see these edge matching techniques that people are using. And during edge matching, we are talking about this continental slope, rather we are talking about the coastline, because the coastline changes with time. However, the junction between this continental shelf of land and this is the oceanic crust where they meet, that is the continental slope, it does not change with time. That is why we are talking that point, and during edge matching we are matching those points only. And during this edge matching, what we found, there are certain deficiency and there are some overlapping of area, and that can be explained by stretching and normal faulting during this continental rift. And today we are going to talk about other evidences which are suggesting yes, continents are drifting apart from each other. And the valuable evidence and this quantitative evidence, you can say, it is given by chains of volcanic islands. So, if you see, we have hotspots and hotspot magma, that if you can recall, we are talking about D double prime layer, which is providing the hotspot magma to rise, and this lithospheric plate, it is just moving on it. So, that means at places when this lithospheric plate is moving, the lithospheric system, it is punctured by this hotspot magma. So, if you see, this is the hotspot and this magma is generating and it is puncturing the lithospheric system, and finally, we are getting an volcanic island here. And if you go in this way, this arrow is given, that means the plate is moving. So, this is the oldest one, and finally, gradually it becomes younger and younger, and this is the newest one. So, the distance between these two and this age difference between these two, we can use to say about what is the rate of plate movement. So, similarly, this hotspot system in the specific, not only they say about this quantitative plate motion, that also say about the directional change of plate motion with time. For example, if you see here, this earlier or this oldest segment, whatever it is shown here, the oldest hotspot segment is here, and its direction, for example, it is north south, and at this point you see the orientation is changing, it is to northwest to southeast. So, that means it indicates that earlier the plate motion was in this direction and now the plates are moving in suppose different direction. So, that means directional change of a plate that can also be studied from this hotspots association. But unfortunately, this method can be used up to early Cretaceous. The reason being, if you remember when we were talking about this convergent system, the oldest oceanic live lithosphere we are having is the up to this early Cretaceous, around 200 million years or so. So, that means beyond that, this lithospheric system has already been subducted and destroyed, and we do not have that one. So, that is why this method of hotspot providing this continental drift hypothesis, that means support to continental drift hypothesis, is only valid up to this early Cretaceous system. And this method gives an absolute reconstruction of both latitude and longitude of this plate motion. Then another evidences is the stratigraphic section, and stratigraphic section, which is mainly people are using up to this Gondwana section, because beyond that the stratigraphic section, it is highly deformed and it is obscured. So, now up to this Gondwana or particularly the Gondwana system, it is less deformed or undeformed, and you will get a uninterrupted section. So, that people are using from different part of the world. If you see here, these are the different stratigraphic sections from different geographic locations. This is Argentina, Brazil, then like this you are coming to the Australia and Tasmania. So, that means all around this world people are using this Gondwana system for correlation, and they are finding that coal, tillite, then Glossopteris flora bearing sequence and Gangamopteris flora bearing sequence, they are well correlating with each other. And now these continent or these geographic regions, they are thousands kilometer apart from each other and across this oceanic system. So, that means it is indicating these land masses once upon a time were together, and later on they are drifted and separated. And this, for this correlation, geological correlation, they have used marker bed of tillite, coal and Glossopterid and Gangamopteris bearing flora that we have already discussed. Then addition to that, another evidence is the metallogenic province. Metallogenic province, you know, there are geographic regions which are very prone to metallogeny in geological past. When we are talking about this crustal evolution, probably you can remember, we are talking about different regions of this earth, they were prone to magmatism, large igneous province and metallogenesis. And those metallogenic province, they were confined to particular geographic region at that time. Now imagine we have different continents, once upon a time they were together and there was metallogenesis in this region, for example, and now they are separated. So, once they are separated, that means the same metal which is found here, that can be found here. Similarly, from this side and this side may be similar, and from Madagascar to India it will be similar. So, that means this metallogenic province having similar metallogenesis, they are this good indicator for continental drift hypothesis to prove. Then another is the climatic region, distribution of this climatic region on the earth. We know these climatic regions, they are latitude controlled. So, different latitudinal starting from 90 to 0, that means equatorial region to polar region, this system or this earth's surface has been divided into different climatic zones, and those climatic zones, they produce a particular type of rock characteristics of that climate. For example, coal, it is a product of warm and humid climate, and ice, it is the product of cold climate. So, we are not expecting that ice site can be formed at the equatorial region. So, now if it is happening so in the geological past, in the rock record, if you are getting this ice deposit and tillite, it is in the equatorial region, that means it definitely says that once upon a time there was either climate was changed here, or this region which was in a cold region, now it is drifted to here. So, that means this latitudinal region like cold zone, then temperate zone, then subtropical zone, then tropical zone, these are this classification, and product of that means I am talking about the sedimentary product, sedimentary rock product, there are characteristics of this climate and their distribution that says that once upon a time these regions were not here or not in this proper climatic zone where they are lying now. For example, some of these climatic indicators in this world, in the rock record, there people are using, that is carbonates and reef deposit. They are mostly, it is warm water deposit, because if you remember when we were talking about the fore-arc back-arc basin, that is due to warm water environment, the fore-arc basin was prone to generate this carbonate platforms or the reefs. So, this carbonate deposit, it is particularly the reef carbonate reef deposit, that is of warm water deposit. So, if nowadays if we are getting in rock record in Antarctica, we have this carbonate reef deposit, that definitely it says it is not the product of that place. So, this continent has moved. Similarly, evaporite, it is a hot arid condition. So, Red bed, it is the sediments containing hematite under oxidizing condition. So, presently found in latitude less than 30°. Coal, it is the vegetation accumulation rate exceeds than removal, and it is tropical rainforest. So, that means similarly there are phosphorite, bauxite, glacial deposits. So, they are characteristics of particular climatic regime. So, deviation from that means it is indicating either there was past climate, that means promoting for their formation, or the region which was in a different climatic region, now they drifted to this. So, any exception from this above condition indicate the shift of climatic condition or shift of depositional site. So, that is the continental drift. Then another very prominent support for continental drift, it is the paleontological evidences. Paleontological evidences, if you see, that is it has affected the distribution of ancient animals and plants by creating barriers to their dispersal. So, once upon a time, if you see, when these continents were together forming this Pangea, there was free passage of animals among these. So, now they are separated. So, once they are separated and they are separated by huge ocean inside, so this become a barrier for their movement. So, their restriction is now within a particular continent. So, that is why growth of an ocean between these two fragments of the supercontinent, which prevented migration between them and the terrestrial life forms. The past distribution of tetrapod implies that there must have been easy communication between all parts of the Gondwana and Laurentia. So, here the Gondwana and Laurentia, that was well connected, and these tetrapods that could pass easily, that can distribution is easy and uniform everywhere. However, nowadays they are separated. That remains of the early Permian reptile Mesoceras are found in Brazil, South Africa, like that. Here this is a very nice representation by this Glossopteris, this green part, then Mesoceras, this is the blue part, and this Listroceras, this is the red part. Now, you see, once upon a time when these continents were together, their distribution was among these. Now, you see, their distribution is different. That means, you are getting this fossil record in those areas and also in this marine sequence here. So, it is not possible. So, that is why it is believed that those continents were together and they are separated, and this is also the same thing which is shown in different image. Not only for this Mesoceras and other reptiles, this plant fossil also they are playing major role, and they are major indicator of this continental drift, because their distribution also climate controlled. So, the widespread dispersal of marine invertebrates can only occur in the larval stage, and when they are part of this plankton. And for most of these species, the larval stage is too short lived that it cannot cross this huge ocean inside. So, that means, you see, if we believe that no, it can be possible that maybe in the larval stage these organisms they have crossed this ocean like that. So, crossing a ocean of 5,000 kilometer width, it is a time taking procedure, and this time taking procedure which is, that means, more than the larval stage, and in the larval stage it is very too short time. So, that means, though it is possible in the larval stage that we believe or we can believe, but due to the shortage of this time for the larval stage, it is not possible to believe that yes, during the larval stage these organisms have travelled across this ocean and they are distributed among this continent. Then, continuing with these paleontological evidences, there are very prominent fossils. One is the trilobite, which is Cambrian, and another here it is the ammonite fossil, which is of Jurassic. That an index fossils you can say, that is very, that means indicator of this continental drift theory, because their distribution here you can say between ammonite species is found in Madagascar, Africa indicates that shallow seas could have been existed between these regions in the Jurassic time. So, during this shallow sea which was existing there, because if you see this time it is indicating the time of that is the separation between Madagascar and India, and when there was rifting taking place, this shallow sea was existing. So, probably that time it is indicating that their distribution would be. So, that means all those paleontological evidences, they are saying that yes, continents have drifted apart from each other. And apart from this paleontological evidences, climatic zones, metallogenic province like that. So, there is a very prominent example or prominent supporter of this continental drift. It is called the paleomagnetism. So, last class if you remember, we are just initiated what paleomagnetism is. So, this paleomagnetism and polar wandering curve, they are very good indicator, and this is not the qualitative indicator, this is the quantitative indicator too about this continental drift theory. So, this fossilized magnetism, what this fossilized magnetism is there. So, now imagine we have a globe, we have earth and we have this north south geographic pole and we have magnetic poles also. So, as the magnetic pole is existing, we have magnetic lines of force, just it is like this, and any mineral which is forming on the surface of this earth, when their magmatic origin or igneous origin, when it is cooled below the Curie point, when it is solidified, so it freezes this existing magnetic field on its surface within the magnetic minerals, and this direction of magnetization, it is fixed and depending upon the magnetic latitude, the inclination that is proportional to the magnetic latitude where this is crystallized. Similarly, in a sedimentary basin, when the sediments are getting deposited, the fine grained particles, particularly these magnetic particles, when they are settling down, they are also oriented themselves according to the existing magnetic field. And once they are freezed within this rock record, that can be used, that is called fossilized magnetism, and that magnetism can be used to study this paleolatitude of this rock formation, and that is a very good indicator of this continental drift. So, when paramagnetic substance is placed in weak external magnetic field such as the earth field, the atomic dipole rotate so as to become parallel to the external field direction, and this induced magnetization is lost when the substance is removed from the place as the dipole returns to their original orientation. And the paramagnetic minerals are capable of retaining a record of this past direction of Earth's magnetic field when they freeze below the Curie point, and Curie point, it can be established or it can be defined the temperature where a material's permanent magnetism changes to induced magnetism. And rocks can acquire natural remnant magnetization, it is called NRM, by several ways, that is called primary ways or secondary ways. Primary ways, that means when the rock form, the magnetization is imposed in that, and that is the thermo remnant magnetization. That means the thermo itself, it is saying about the temperature. So, that means it is the minerals which are forming or the rock which is forming from lava, when they are cooling down below this Curie temperature, when they are getting solidified, these magnetic minerals like magnetite and other ferromagnesian minerals, they are orienting themselves, and this according to the earth's existing magnetic field. And then another is called DRM or depositional or detrital remnant magnetism. So, that term itself, it is saying, talking about the sedimentary rocks. So, the sedimentary rocks, when they are depositing during settling down in the water column, they are orienting themselves, particularly these magnetic minerals, they are orienting themselves according to this earth's magnetic field, and they are responding to this magnetic field and orienting likewise. Another is the CRM, that is chemical remnant magnetism, that means it is talking about some chemical reaction, that means there is the diagenesis, that means after the deposition, when the diagenetic reaction taking place within the sedimentary rock, some new minerals are created like magnetite, hematite. So, this magnetic mineral if you are creating, so those magnetic minerals they are orienting themselves according to the Earth's magnetic field. And this is isothermal remnant magnetization, that means we are talking about lightning effect, thunderstorm lightning effect, when there is lightning effect to this earth surface. So, it magnetizes the rock where it falls. Then VRM, that is viscous remnant magnetization, that means when these magnetic minerals are placed under weak magnetic field for millions of years, its magnetization changes and it is adopt the new magnetic field. So, that is all about this magnetization processes, and we will talk in detail how this magnetization process they help in plate tectonics and particularly providing evidence about this continental drift. So, talking about this thermoremnant magnetization or TRM, it is acquired as the rock cools from its motion state to below the Curie temperature, which is realized after solidification. At this stage, it ferromagnetic minerals picks up this magnetism of the same sense as the geomagnetic field that time, which is retained during subsequent history. So, example is the magnetite in basalt. For example, if you see here, we have lava which is coming down, and you see this there is no magnetization because it is above the Curie temperature. So, once this temperature is going down, so once it is reaching below this Curie temperature, so this minerals, this magnetic field is freezed, and that freezing it is according to this earth existing magnetic field. So, for example, we have different basaltic flow layers. For example, we are talking about the Deccan Trough, we have different basaltic flow layers, and here when this magnetic minerals which was formed here, this was reverse magnetized system was there. So, that means we will find reverse magnetic axis here or magnetic minerals are here, but suppose during another flow there is a normal magnetization. So, we will get this magnetic orientation of opposite to this previous one. So, accordingly there will be normal reverse stratigraphic sequence, and it is used as magnetostratigraphy to study. So, that means during subsequent basaltic eruption formation of this basaltic rock, this magnetization is varying with time, and that is best studied in the ocean floor, because we know the ocean floor is the carpet of basalt, it is continuously forming. So, during its formation from starting from the 0 to this early Cretaceous, because beyond that we do not have this ocean floor life. So, up to that this whole carpet of basalt can be divided into different segments according to this normal and reverse magnetic field. So, here we are talking about the DRM, datatral or depositional remnant magnetization. As the sedimentary particles settle through this water column, any ferromagnetic minerals present align in the direction of this ferromagnetic field. On reaching the bottom of the particle, it is flattens out, and if of elongate form, preserve the azimuth of this geomagnetic field, but not the inclination, because it is sedimentary system which is squeezed system that is settled down. So, its inclination is not preserved, however, the azimuth, that the direction of this magnetic field, it is preserved. Then chemical remnant magnetization, that already we have discussed. This is the magnetization which is remained in the diagenetic reaction mineral product, particularly the hematite when it is producing due to diagenetic reaction. And if you see here, we have different sandstones, we have red sandstones, and this red sandstone is nothing, it is the oxidized product of that is oxidized product is nothing, this is the magnetite or hematite which is forming, and those minerals are this minute magnetite minerals which is forming here, these minute hematite minerals which is forming here, they are orienting according to this earth's magnetic field. Then isothermal remnant magnetization, that means during this thunderstorm or lightning, when it is falling on this rock, you see how this rock system is changed, and this is called this isothermal remnant magnetization. And very important here to note it that this isothermal remnant magnetization, it is easy to distinguish because no preferred orientation of magnetic axis, nothing. So, that means very haphazard orientation. So, if you are keep on measuring this magnetization in an area, if you are coming to an area which is affected by this lightning event, so you will find that means suddenly your magnetometer it will give haphazard reading. So, this type of area can be distinguished from the surrounding which part that means the actually it is affected by this lightning effect. Then another is the viscous remnant magnetization or VRM. It is when this rock is placed under weak magnetic field for millions of years, this natural remnant magnet it acquires the external field direction, and the natural remnant magnetization of ultramafic igneous rocks that can alter in this process. So, that means now you see we have any subsequent magnetization in rocks are regarded as noise, and because to conduct this paleomagnetic pole position, only the initial magnetic field is required. Otherwise, there are number of times this magnetic reversal normal and some lightning or something like that. That means all they are the noise, they are superimposed on that. So, this geologist or those people who are working in this paleo pole position construction, reconstruction of the paleo pole position, their work is to first clean this sample. So, cleaning that means it is called magnetic cleaning. That means subsequent superimposed magnetic fields they are cleaned out, and we are going to this original magnetic field, that means when this rock was formed. So, this paleomagnetic measurements provide the intensity, azimuth and inclination of this primary remnant magnetization. That means subsequent cleaning we are reaching to this product, that is we are getting this azimuth, intensity, inclination of this primary remnant magnetization, which reflect the geomagnetic parameters, that time and place at which the rock was formed. Inclination I can be used to determine the paleo latitude, that is phi at this formula 2 tan phi equal to tan I. So, in this formula we can calculate which geographic region it was formed. So, this CRM, TRM and DRM tend to be hard and remain stable over long period of time, whereas certain secondary components of NRM, notably the VRM, are soft and it is lost relatively easily. So, it is thus possible to destroy this soft component and isolate the hard component of this magnetic field or magnetization through this magnetic cleaning procedures. So, once the magnetic cleaning is complete, whatever this result we are getting, we are using it to reconstruct the paleo pole position of this rock, where the rock was formed. So, now you see, if a paleomagnetic study provides a magnetic pole position different from this present pole, it implies that either that the magnetic pole has moved throughout this geologic time, that is the magnetic pole has wandered relative to the rotational pole or the geographic pole, and that is why it is called apparent polar wandering or APW. Or if the pole have remained stationary, that the sampling site has moved, that is the continental drift occurred. So, this first one is ruled out. Why it is ruled out? Because it appears that wandering of magnetic pole away from this geographic pole is unlikely, because all these theoretical models for this generation of a field predicts that dominant dipole component paralleling to this earth rotational axis. So, that means the first component it is ruled out, that means there is no movement, or that means no you can say a considerable movement of this magnetic pole from this geographic pole. So, that means now the other option is that means the sampling site has been changed. So, that means this continents had moved. So, consequently the paleomagnetic study can be used to provide a quantitative measurement of this continental drift. So, that means it is not that this continent was fixed and the pole has moved. So, it is now this pole is fixed and the continents has moved. So, this is the correct one. And the observation that apparent position of this pole at different rocks of different ages from the same continent demonstrate that these continents have moved over the subsurface on the surface of this earth. Now, imagine we have a stratigraphic succession and we are taking a sample from here and we are taking a sample from here, and we are taking a sample from here. So, that means in the stratigraphy column different interval we are collecting samples, and through this magnetic cleaning we are getting some result, that means some latitude, longitude, like that. So, that means we can say when this sedimentary layer was deposited, which was the position of this region geographically, which latitude, longitude, and when this was deposited, what is the latitude, longitude. Similarly, when this was deposited or this layer was deposited, what is the latitude, longitude, and now that means similarly this position of the depositional site with respect to this latitude, longitude can be reconstructed using this formula tan I equal to 2 tan phi. So, this is the key formula that this paleo pole position can be reconstructed. So, apparent polar wandering paths can be used to interpret the motion, collision, disruption of continents, and are specially useful for pre-Mesozoic continents whose movement cannot be traced by pattern of magnetic lineation in their surrounding ocean basins. So, now you see the ocean basin up to the early Cretaceous we can move. So, whatever this continental drift or the seafloor spreading, that can be studied using this paleomagnetism, that is up to the early Cretaceous in the ocean floor. But beyond this early Cretaceous, that means beyond Mesozoic, if we want to study this position of a place, so we have to go to this continent, because no more ocean floor older than that it is existing. So, this pre-Mesozoic continental reconstruction, that is from lake sediments, we can get from this paleomagnetic study. Suppose for example, this is an area we have continent, for example, we have a continent and two different position we have collected sample. So, whatever this position we constructed, yes, this is the latitude, longitude condition. So, now it is moving. So, we are collecting sample, again this is the latitude, longitude. So, it is collecting sample. So, that means now you see these 2 points are getting closer. So, now at this point one is moving in this way, another is moving that way. That means its latitude changes, its latitude changes. That means what I can say, here the rifting starts, isn't it? Up to this latitude, longitude, the motion was together. However, from here it is a separate basin, this become a separate basin, and two moved independently to opposite direction. And after some millions of years, after movement of here and there, so now you see at this point again they are colliding. So, because their latitude, longitude is same. So, we can say these two plates which was earlier together, they rifted, they drifted, and they collided. So, that means whole plate tectonics that we have studied so far, rifting, drifting, collision, that can be studied by these paleomagnetic studies. So, thank you very much. We will meet in the next class.